Orange dwarf stars with masses between 50 to 80% of the Sun and surface temperatures ranging from 3,500 to 5,000 Kelvin occupy a unique position between G-type stars and smaller red dwarfs. Their remarkably long lifespans, spanning billions to even hundreds of billions of years, provide ample time for biological evolution on surrounding planets. These stars emit less energy and light compared to the Sun, allowing the habitable zone to be closer, which aids in maintaining liquid water. Additionally, their reduced ultraviolet UV radiation helps protect planetary atmospheres. As a result, orange dwarf stars can offer a stable energy source, creating ideal conditions for life to develop on oceanic planets. Their long-term stability contributes to sustainable climates and living environments. Moreover, the inward migration of planets significantly alters their distances from these stars. Initially, a planet may be located about 0.5 to 1.0 astronomical units away, but as migration completes, this distance can shrink to 0.3 to 0.5 astronomical units. Such changes illustrate the evolution of a planet's orbital dynamics and its climatic conditions, which are crucial for the potential emergence of life. The graph indicates that orange dwarf stars exhibit the highest suitability for chemosynthetic life, which is advantageous for our designed planet orbiting such a star. These stars are long-lived and have lower energy output, providing balanced energy to the planet's surface and oceans, creating an ideal environment for chemosynthetic life. Yellow dwarf stars are also quite suitable, though not as much as orange dwarfs. Red dwarf stars appear quite suitable as well, though not as favorable as orange dwarfs. Red dwarfs can be more active, potentially leading to higher radiation levels on the planet. Red giants, blue supergiants, and variable stars appear highly unsuitable for chemosynthetic life due to their shorter lifespans and instability, which do not provide the long-term conditions needed for the development of such life. In conclusion, the data confirms that our planet, orbiting an orange dwarf K-type star, is highly suitable for chemosynthetic life. These stars provide stable, long-term energy sources that can support the development of life in the depths of the planet's oceans. Planets form in the outer regions of a star system within a protoplanetary disk. Initially far from their star, 1 to 2 astronomical units, they grow and interact with the disk, causing them to gradually migrate inward. As they stabilize at around 0.3 astronomical units, conditions become suitable for chemosynthetic life due to favorable temperatures and atmospheric pressure. Proximity to the star leads to temperate ocean temperatures and hydrothermal vents, creating energy sources for life. Ultimately, the planet achieves a stable orbit in a habitable zone. Deep within the Milky Way galaxy lies a fascinating region known as the Galactic Habitable Zone, GHZ. A planet located here would benefit from an abundance of essential heavy elements and be shielded from threats like supernovas and black holes. The GHZ is a middle region of the galaxy, approximately 26,000 light-years from the galactic center. This area boasts conditions optimal for life, rich in heavy elements vital for planet formation. One of the most promising locations for such a planet is the Orion Arm, which is home to our solar system. This region, also about 26,000 light-years from the center, provides an ideal balance of safety and elemental richness. The Orion Arm is abundant in essential gases, such as nitrogen and water vapor, crucial for life. Its distance from the galactic center protects it from harmful radiation and black hole activities, fostering a stable habitat. Additionally, the presence of K-type orange dwarf stars increases the likelihood of finding similar planets, enhancing the potential for life. In the Orion Arm of the Milky Way, within the galaxy, a planet about 26,000 light-years from the galactic center could offer the perfect conditions for chemosynthetic life to thrive, making it a remarkable candidate for the search for extraterrestrial life. Atmosphere, the outermost layer represented by the light blue area, indicating the mixture of gases present on the planet's surface and the density of the atmosphere. This layer is one of the most important components affecting the planet's weather conditions and energy balance. Ocean surface. This light blue layer, located just beneath the atmosphere, shows the water mass on the planet's surface, namely the ocean. Given that this planet is an ocean planet, the water surface will cover a vast area. Deep ocean, represented in a darker blue color, this layer shows the deep oceans located beneath the surface oceans of the planet. With a depth of 10 kilometers, this layer includes regions with hydrothermal vents, particularly for chemosynthetic life. Ocean shell. This layer defines the boundaries of the planet's deep oceans and forms the outer shell of the oceans. Chemosynthetic life is expected to be found in areas close to this layer. Planet shell. The planet's shell, brown layer, located just beneath the ocean, shows the terrestrial structure of the planet. This layer is the outermost layer of the planet's internal structure and determines tectonic movements that may occur on the surface. Mantle. The inner layer, shown in dark brown and gray tones, is referred to as the mantle. This layer makes up a large part of the planet's subsurface structure and controls the geological activities of the planet. Core. The innermost gray area in the diagram represents the planet's core. The core is the fundamental layer that controls the planet's magnetic field and internal heat. This planet has a thick, dense atmosphere rich in carbon dioxide, CO2, and methane, CH4, causing light to scatter and giving the sky a reddish-orange hue, especially during the day. Orbiting an orange dwarf star, it experiences mild seasonal changes due to an axial tilt of 10 to 20 degrees, with less extreme temperature variations than Earth. The dense atmosphere leads to stronger winds and more intense hurricanes, while its 10-kilometer deep oceans provide abundant water vapor, energizing storm systems. Surface temperatures range from 0 to 10 degrees Celsius, with warmer depths near hydrothermal vents, maintaining a temperate climate. The atmosphere of this planet is primarily composed of nitrogen, 70 to 80%, which stabilizes the atmosphere and maintains pressure. Carbon dioxide, 10 to 15%, and methane, 1 to 5% levels, are crucial for chemosynthetic life, serving as key energy sources for organisms in deep oceans. A small amount of oxygen, 1 to 5%, is present, sufficient to support life, though not in excess. Hydrogen sulfide, 0.5 to 1%, is important for chemosynthetic organisms, especially near hydrothermal vents. Water vapor, 1 to 3%, helps regulate humidity and temperature, while a small proportion of argon, 1 to 2%, contributes to atmospheric stability. This gas composition supports the potential for life on a planet orbiting an orange dwarf star. The ocean on this planet must be deep enough to support effective hydrothermal vents, providing vital habitats for chemosynthetic life. A depth of 10 kilometers is ideal, allowing these vents to thrive while creating the necessary high-pressure conditions. In terms of density, ocean water is influenced by the planet's gravity and its chemical composition. Earth's ocean water has a density of about 1.03 grams per cubic centimeter. However, with this planet's gravity being 2.5 times that of Earth, its ocean is likely to have a slightly higher density, though not drastically different. A suitable density range for the ocean would be between 1.05 grams per cubic centimeter, adjusted to align with the planet's stronger gravitational pull. With an axial tilt of 10 degrees to 20 degrees, seasonal changes are milder than on Earth. This results in stable equatorial temperatures and more pronounced seasonal differences at the poles, where it remains cold. Oceans regulate the climate, maintaining equatorial temperatures around 5 to 10 degrees Celsius, while polar regions drop below 0 degrees Celsius. Ice forms at the poles due to reduced sunlight, creating permanent ice cover, though summer melting is less dramatic. Hurricane potential exists in equatorial regions, but storms are less intense due to the lower tilt. Fog is common near the equator and at the poles, while snowstorms are frequent in polar areas during winter, but rare near the equator. Orange dwarf stars, K-type stars, are cooler and smaller than Earth's G-type stars, emitting less energy and keeping planet surface temperatures around 0 to 10 degrees Celsius. This limited energy affects the atmosphere's overall temperature, with most light reaching the planet being in the infrared and orange wavelengths, creating a unique heating balance. The low energy output leads to ice formation, particularly at the poles, where temperatures can drop further in winter, resulting in large ice sheets. Vast oceans promote sea ice formation, especially at the poles, along with seasonal ice coverage. Atmospheric pressure differences create winds, with high pressure in the cold polar regions and low pressure near the warm equator. This results in strong wind systems and frequent storms, especially in areas with warm ocean currents. Continuous evaporation from the oceans produces high humidity, leading to precipitation in colder regions and tropical rainstorms near the equator. In summary, the low energy output of orange dwarf stars maintains a cool climate, with seasonal changes affecting polar ice sheets and creating dynamic atmospheric conditions. If the planet orbits its orange dwarf star at a distance of 0.3 astronomical units, the star's gravitational pull can generate sufficient tidal energy. With oceans that are 10 kilometers deep, tidal waves can have more pronounced effects, as this depth provides an environment conducive to storing the energy of ocean currents and tides. At a rotation speed of 0.2094 radians per second, the prominence of tidal waves can increase, allowing for wave accumulation. The gravity is estimated at approximately 12.1 meters per second, which is higher than Earth's, contributing to a denser atmosphere. When the atmospheric density reaches 1.5 grams per cubic centimeter, it can lead to the formation of thicker clouds and adverse weather conditions. High pressure and temperature variations can influence cloud formation, resulting in heavy rainfall. Additionally, elevated humidity levels can cause dense fog and precipitation, creating a rich ocean ecosystem that provides essential nutrients and energy sources for chemosynthetic life. As you descend into the depths of this enigmatic oceanic planet, the serene surface, with temperatures ranging from 0 to 10 degrees Celsius, gives way to a chilling expanse where temperatures plummet below 2 degrees. In this abyssal realm, geothermal vents punctuate the ocean floor, releasing plumes of superheated water that reach temperatures between 100 and 400 degrees Celsius, serving as beacons for life in an otherwise frigid environment. In this extraordinary habitat, the juxtaposition of freezing depths and scalding geothermal activity allows life to adapt and thrive in conditions that seem inhospitable, showcasing nature's remarkable resilience and ability to flourish against all odds. Hydrothermal vents found on the ocean floor near magma and typically located along mid-ocean ridges create vital habitats for diverse life forms due to tectonic activity. These structures, composed mainly of sulfur and iron, emit black smoke and can reach temperatures of up to 400 degrees Celsius. At the core of this extreme ecosystem are sulfur-oxidizing chemosynthetic bacteria, which convert inorganic compounds into energy and form the foundation of the food web. These bacteria coexist with giant tube worms and mollusks, creating a vibrant community that highlights the remarkable adaptability of life in one of Earth's most extreme environments, where sunlight is absent and chemical energy prevails. The most pressure-resistant ocean creatures live close to hydrothermal vents. One of them is the anglerfish. This fish can hunt in dark waters thanks to the flashlight on its head. The most pressure-resistant ocean creatures inhabit the depths near hydrothermal vents, with the anglerfish being a prime example. This extraordinary fish has adapted to its dark environment by developing a bioluminescent lure on its head, resembling a flashlight. This unique feature allows the anglerfish to attract prey in the pitch-black waters, showcasing its remarkable adaptations to one of the ocean's most challenging habitats. The most pressure-resistant ocean creatures live close to hydrothermal vents. One of them is the anglerfish. This fish can hunt in dark waters thanks to the flashlight on its head. The most pressure-resistant ocean creatures inhabit the depths near hydrothermal vents, with the anglerfish being a prime example. This extraordinary fish has adapted to its dark environment by developing a bioluminescent lure on its head, resembling a flashlight. This unique feature allows the anglerfish to attract prey in the pitch-black waters, showcasing its remarkable adaptations to one of the ocean's most challenging habitats. Some hydrothermal vents, rich in calcium, emit white smoke and operate at lower temperatures than their black smoke counterparts. In these unique environments, calcium-oxidizing bacteria thrive by forming symbiotic relationships with other organisms. This cooperation is vital for sustaining life, highlighting the remarkable adaptability of organisms in the extreme conditions found at hydrothermal vents. Hydrothermal vents host a diverse array of marine life that can withstand the high pressure of the ocean floor. Oysters, shrimps, mussels, crabs, and sea snails thrive in this extreme environment alongside starfish and sea cucumbers. This unique ecosystem benefits from the nutrients and chemical energy provided by the vents, highlighting the resilience and adaptability of life in harsh conditions. Geysers are fascinating natural phenomena formed by the periodic eruption of seawater heated by magma beneath the Earth's surface. When this hot, mineral-rich water erupts, it quickly comes into contact with cooler seawater, causing the minerals to solidify and create striking mineral deposits and chimneys. Surrounding these geysers, thermophilic bacteria thrive in the extreme temperatures, contributing to a unique ecosystem. This dynamic interplay between heat, minerals, and life highlights the remarkable adaptations of organisms in such extreme environments. Ocean trenches and mid-ocean ridges are formed by the movements of oceanic plates. In these regions, inorganic substances create a suitable environment for life. Ocean trenches and mid-ocean ridges are intriguing geological features formed by the movements of oceanic plates. These dynamic regions provide nutrient-rich environments due to the inorganic substances released from the Earth, supporting diverse ecosystems and showcasing the remarkable adaptability of life in extreme oceanic conditions. A planet with a mass 2.5 times that of Earth may have a rotation period slightly longer or shorter than 24 hours, potentially ranging from 20 to 30 hours. At 0.3 astronomical units from its star, the planet would experience a shorter year, typically lasting 30 to 50 Earth days. While gravity affects the surface pull, it doesn't change time perception, though high gravity can influence local conditions. The rotation speed determines the length of a day, which could be around 30 hours, resulting in longer days and nights. Briefly, our ocean planet orbits an orange dwarf star at a distance of 0.3 astronomical units and is 2.5 times larger than Earth. Its slow rotation speed of 0.2094 days suggests a unique day-night cycle that could influence its climate and ocean currents. With an atmospheric density of 1.5, the planet supports a rich array of chemosynthetic life around hydrothermal vents, where nutrients and energy abound. This environment fosters a complex ecosystem with diverse forms of life uniquely adapted to thrive in extreme conditions beneath the ocean's surface.